Hello everyone. So far we covered two main topics in calculus, including functions and limits, and today I'm very happy to start the video on derivatives, and I'm going to start with the definition of derivatives. The derivative of a function like f of x with respect to x is the function f prime of x actually, and we can define it by a limit as we can see in here. So we have to actually make a limit in the form of f of x plus h minus f of x over h. As I said before, a derivative is actually an indeterminate form of limit, and we have to use some sort of algebraic simplifications in order to solve that limit. Once we solve that limit, basically we obtained the derivative of that specific function. In general, a function like f of x is called differentiable at x equal to a if the f prime of a exists, and f of x is called differentiable on an interval if the derivative exists for each point in that specific interval. There is a relation between continuous function and the derivatives. Basically, if the function of f of x is differentiable at x equal to a, then f of x is continuous at that value of a. Let's look at two examples related to the derivative of a function and the definition of the derivative. So the first example that I have in here is basically f of x equals to 2x squared minus 14x plus 25, and I'm going to use the definition of the derivative in order to find the derivative of this function. So based on the definition of the derivative, we have f prime of x equals to the limit of f of x plus h minus f of x over h when h is approaching to 0. Now we have to plug in x plus h instead of x inside this function, and therefore we will have the limit of 2x plus h squared minus 14x plus h plus 25, and then it's going to be minus the whole function, which is 2x squared minus 14x plus 25 over h when h is approaching to 0. Okay, now if we plug in h equal to 0 in here, it's going to be again an indeterminate form, and what we have to do first, we have to expand the terms that can be actually expanded, like x plus h squared, and the other one is this multiplication minus 14x plus h. So from there we will have f prime of x, let me use another color, equals to, if we expand the first term, it's going to be 2x squared plus 4xh plus 2h squared, and then the second term is going to be minus 14x minus 14h plus 25 minus 2x squared plus 14x plus minus 25 over h when h is approaching to 0. Now this 2x squared will be cancelled with this 2x minus 2x squared that we have, minus 14x is going to be cancelled with positive 14x, and positive 25 is going to be cancelled by minus 25. So from there we would have f prime of x equals to the limit of the remaining terms is going to be 4xh plus 2h squared minus 14h, and then over h when h is approaching to 0. Now if we plug in 0 again in there, this is going to be 0 over 0, which is an indeterminate form. But what we can do the factoring, which will result in the limit of h 4x plus 2h minus 14 over h when h is approaching to 0. This h will be cancelled from top and the bottom. Now it's time to plug in 0 in there, and the final answer is going to be 4x minus 14. So as you noticed in here, we have used the definition of the derivatives, which is actually a limit, which basically generates an indeterminate form of a limit, and with some algebraic simplification we could find the answer of this limit. In our future videos we will see how we can use the rules in derivative like power rule in order to find the derivative of polynomial functions as you noticed in here. Let's look at the second example that I have for today, which is f of x equal to absolute value of x, and we want to find the derivative of this specific function at x equal to 0. So again we have to use the definition of the derivatives, which is actually a limit. So we can make that in the form of f prime of 0, and then now instead of x we have to use 0. It's going to be f of 0 plus h minus f of 0, and this is going to be basically the limit over h when h is approaching to 0. And what we will get in there is going to be the limit of 0 plus h, the absolute value, minus 0 over h when h is approaching to 0, and this will generate the limit of h over h when h is approaching to 0. If we look in this function now, we have an absolute value over h, and we want to find this limit. If we plug in 0 in there, this is going to be an indeterminate form. But you know, when we have basically the absolute value, this function is in this form. The absolute value of h is actually h if h equal or bigger than 0, and it is minus h if basically h is less than 0. So what we can write in here now, we can actually have two basically parts for this function, and it's going to be the limit of from the top part or from the bottom part. Let's start from the bottom part. It's going to be the limit of h over h when h is approaching to 0 from left side. Basically we are in this region now, and it is going to be negative h over h. So this h is going to be cancelled from top and the bottom, and the answer is going to be minus 1. Okay, so now if we look at the top part of this function, when h is equal or bigger than 0, the limit is going to be in the form of, again, the same thing we can write based on what we have over there, h, and h is in positive side, basically 0 positive, which is going to be h over h, and this is going to generate 1. So if we look, the limit of this function doesn't exist, because if we look at from the left side, it will generate -1. If we look at the positive side, it will generate positive 1. So it means that this limit doesn't exist, and when the limit of a function doesn't exist, it means that we cannot find the derivative of that function. So using the definition of derivatives in here helped us to first understand this limit doesn't exist, as we looked previously in the actual section of limits. And once, as I said, the limit doesn't exist, we cannot get the derivative of that specific function. Thank you very much for watching this video. We will cover the concept of derivatives with many more videos, and you will see different basically rules related to the derivatives, as well as the applications of derivatives in near future.